Hello and welcome to another lecture for my class, PSYC 440/640, which is a class called Experimental Methods, but it's really more of a class about univariate statistics. This lecture that I'm recording now, I set for a class that occurred right after the holiday for Martin Luther King Jr. Day, and this webcomic from PhD Comics seemed appropriate because I think in academia it's sometimes hard to take a day off, even for a very good reason, like honoring one of our nation's most important civil rights leaders. Anyway, with that in mind, the title for today's lecture is Introduction to Models, and it is, well, basically just that. It's an introduction to some very basic ideas that have to do with making statistical models. By way of an overview, we're going to begin by presenting what I call the basic formula, which we use as kind of our starting place for thinking about statistical models. Then we're going to step to the side slightly and talk a little bit about descriptive statistics, which you'll see the reason why we do that. And then towards the end of the lecture, we'll present a very simple model, which is just the sample mean, which we use as a way of estimating the population mean. And I'll talk a little bit about how we assess the fit of that model. Okay, so introduction to models, building stuff, making little representations of other larger things. The basic formula is just this. It's data equals model plus error. And in different ways, we're going to encounter this basic formula throughout all the different lectures in this semester. So let's take a look at the different parts. The first part, data, refers to the variables that we're trying to describe, specifically the outcome or dependent variable that we're trying to describe. So we have a measure of something like depression or overall psychological functioning or some other variable, and each person in our data set has a different numerical value corresponding to his or her level or state on that variable, and we'd like to explain the variability among all those different scores. But again, not all observations have the same value. I mean, it's possible you might have a data set where all the people have the same value for your dependent or outcome variable, but that's very unlikely to happen. It's more likely that just about anything you measure will look different across the members of your sample, different people. You'll be looking at different cases, or even if you're doing some sort of a dependent or repeated measures design, you'll be looking at the same cases over time with the expectation and the likely outcome that those variables that you're measuring will be slightly different at each of those different points. There is variation in our data. This seems to be a really important starting point for our work. And it's one that reminds me of a quote from one of my favorite books by an author named Cowles in 2001. I think this is like the first sentence in the first chapter. It is, "The central concern of the life sciences is the study of variation." We observe that the cases in our data set, the different people or different animals we're studying, differ on some variable we're interested in, or they differ from themselves over time on that variable, and we want to explain that. We want to explain variation in our outcome variable. By the way, that book is Statistics in Psychology, A Historical Perspective, which is far more interesting a book than you might guess from that title. I strongly recommend it. There's some parts he doesn't cover, but he gives a nice overview of the history of statistics in psychology. It's much like Salzberg's book, A Lady Tasting Tea, which I also recommend. So the data that we have, these are the observations in our data set. They're the sample that we've drawn. And although we care about the people in this sample and we're interested in this particular data, of course we're also really interested in the other possible observations that we could have, the other samples we could have drawn from the entire population, or indeed the entire population itself. What about all these other possible observations? We can never make all of the observations, but we can try to describe what they are like, what the distribution of all of these values probably looks like. So we want to describe the distribution of all the data, And we describe it in terms of parameters. Parameters from the Greek meaning like a measure refer to different features or attributes of a distribution of values that we can never know precisely, but which we can describe or we can estimate based on the limited information that we draw from our sample. Thinking about this reminds me of a quote from Salzburg's book, A Lady Tasting Tea, and that quote has to do with a kind of a fundamental shift in thinking that occurred in science in the early part of the 20th century. And the quote is this. It refers to Carl Pearson, who you can see here pictured next to his kind of mentor and buddy Francis Galton. Before Pearson, the things that science dealt with were real and palpable. Pearson proposed that observable phenomena were only random reflections. What was real was the probability distribution. Now what the author means here is that early in science, the idea of making progress, of testing hypotheses and evaluating theories was focused very much on making discrete, often individual observations. So you might observe the cardiac output of the horse heart, or you might observe the position of a celestial body in the sky, or the growth of a colony of fungus on the side of a rock or something like that. And that's what scientists of course still do, but now we don't care as much about those discrete observations as we do about all the possible observations which we could make from the broader population of things that we're studying, whether it's the horse cardiovascular system, or the positions or gravitational relationships of celestial bodies, or the propagation of fungi, or whatever. What we care about is all the data, which we can never have, or we can almost never have entirely, but which we can describe. And Salzburg, who is himself a statistician and kind of a historian of statistics, really emphasizes this as an important, and he calls it kind of revolutionary change in the way scientists thought that occurred kind of at the tail end in the early of the 19th century and the early part of the 20th century. By the way, here's that book. It's really excellent. I highly recommend it. It's much more readable than the Salkind book, although that book is good as well. Gives you a lot of interesting background and context for many of the concepts that we're going to talk about in this class. So just to bring it back to our basic formula again, data is the variation that we observe. We want to describe that data that we have, that variation that we have in our sample. We want to predict or estimate variation in the population. How do we do this? Well, we make a model of some sort, and the model is just our description / prediction about the data. And sometimes in psychology, that model is just a constant, a particular fixed value that is applied to every case in our data set. So in a sense, every case gets the same description, or every case gets the same predicted value, just a fixed number. That's relatively rare, although there probably are some situations in which we could imagine that happening. What's more common is that our model is in some way contingent. It's based on variables, and so these are, for instance, the familiar simple regression equations that you've encountered in other classes. Each person in your data set, each case, has a predicted value on the outcome variable that is related to their level of the predictor variable. So we're predicting people's level of depression based on the amount of alcohol that they consume per week. So for every additional drink that they have, there's some sort of increase or decrease perhaps in their level of depression. These models are contingent in the sense that people get a different predicted value on them based on some single or perhaps multiple predictor variable. Now, I've used the phrase general linear model before to describe a lot of what we're going to do in this class. And what I mean by that is, for the most part, the models we're going to use are straight lines or flat planes or similar sorts of geometric structures. They don't curve, although there may be some exceptions. We'll probably consider a couple curvilinear models here and there. These are rectilinear lines, so that's where the linear part of general linear model comes from. Now, no model is perfect. All models have a certain amount of error associated with them, which we sometimes call error, we sometimes call residuals. Those are the discrepancies between the predicted value that the model says a particular case should have and the actual value that that case has. So you can see here, if you look at this little rather simple scatter plot, for all the data points in this scatter plot, they are all different from the predicted value that we get from looking at the line that passes through that cloud of dots. So there's error associated with each of those data points. For some data points it's rather large, for others it's rather small. There's almost always some amount of error associated with any prediction we make. Recall that unsystematic variation and error are often used interchangeably, so you could talked about this a little bit in a previous lecture. The idea is that we have a certain amount of variation in the outcome variable which we predict based on our model, which is made up of one or more, usually, predictor variables. But there's some amount of variation in the outcome variable which still goes unexplained even after we've done our best to model it, to predict it or describe it. That unsystematic variation we sometimes call error, or we call the residual, or so on. And we use the amount of error that a model has as a way of evaluating it, because as I think we can all sort of intuitively understand, models which have relatively little unsystematic variation associated with them, relatively little error associated with them, are usually better than those which have quite a lot associated with them. By the way, this is just this picture here is just an example of error variation with respect to the prediction made by a curvilinear model. Now, there'll probably be some times in our semester where we do curvilinear models, but for the most part we're not doing those. So just a note there. Kind of like I said before, no model is perfect. All models have error, and for the most part we'd like to reduce error where we can, if we can, because of course reducing error makes data closer to model. If error in this simple formula was 0, then data would equal model, or the model would sort of equivalently would perfectly predict or perfectly describe the data. Now, there are different ways we can try to reduce error, but I think it's easiest to kind of group them into two broad approaches. One approach is to improve the data in our formula, and the other approach is to improve the model. And what do I mean by those two statements? Well, in terms of improving the data, what this often involves is collecting a bigger or better, and by better I mean more representative of the population, sample, or by using better data collection procedures. So for instance, let's imagine we're measuring or we're trying to understand, we're trying to describe or predict the relationship between a particular type of psychological treatment and level of depression. We might, in an effort to improve the data in our analysis, we might gather a larger sample, or a sample that is more representative of the population of people that we're interested in. For instance, the population of all people who go and seek psychological services at outpatient clinics or whatever. Or we might improve our data collection procedures. So instead of using perhaps a poorly constructed kind of quick and dirty self-report measure of depression, we might use a well-validated measure of depression, or we might use a clinical interview conducted by a trained professional, which has less measurement error associated with it, giving us a more precise measurement of each individual person's level of depression. Either of those approaches, or both of them in combination, hopefully would result in better data, which would help tend to reduce the amount of error in our basic equation. Now, this is the focus of research methods classes, and as I've said before, this class isn't technically a research methods class. If you were taking a research methods class, you might spend all semester or more talking about different ways of sampling populations, and different ways of constructing and evaluating different measurements like questionnaires, or sort of reaction time measurements, or laboratory tasks, or psychophysiological tasks, and so on, and so on, and so on. The other broad approach to reducing error involves improving the model. And by improving the model, what I mean is we want to add more predictor variables, more parameter estimates to the model. If you can imagine a case of like a simple regression where we're predicting someone's level of depression based on their use of alcohol. Now, there are other things in the world which are related to level of depression, maybe things like gender or work-life stress or use of other drugs or comorbid anxiety or many other variables. Until we include those variables in our model as one of our predictor variables, as one of our parameter estimates, those variables necessarily lurk, kind of ghost-like, in the error term of our general equation here. When we add them, when we kind of bring them into the fold, making our simple regression now a multiple regression, for instance, where we're predicting people's level of depression based on not just their use of alcohol, but also their work-life stress, or maybe use of alcohol, work-life stress, and also comorbid anxiety, or use of alcohol, work-life stress, comorbid anxiety, and recent health problems, or so on and so on. You can imagine we're creating different models which are incrementally more complex or complicated than the one previous to them. Those models hopefully predict the data, predict people's level of depression better. Each additional predictor variable, each additional parameter estimate, using those two terms interchangeably here, each additional one hopefully gives us more precision in our prediction. Of course, it comes at a certain cost, because each additional predictor variable or parameter estimate makes our model necessarily more complicated. And we're always trying to strike that balance between parsimony and explanatory power, or put more simply, trying to get the most bang for our buck out of the hopefully small group of predictor variables we have. And to the risk of putting too fine a point on it, this is really the focus of our class, especially when we get to Unit 2, where we'll focus on multiple correlation and regression type analyses, where we look at building models which are successively more complicated than one another, comparing those models and trying to decide which one is the best description, explanation, prediction of the data we have. So with all that in mind, let's just linger on one or two more interesting or important points before we move on. Here's an interesting point that maybe I kind of made earlier in reference to that quote from the Salzburg book, but I'll make it again. The interesting idea is, in a sense, we really don't care that much about our sample of data, the people or the non-human animals that we ran in our study. I mean, of course we care about them. Hopefully we're not mean to them or cruel or unethical, and of course we care about them in the sense of wanting to not make mistakes in data collection. But at a kind of a fundamental level, we don't care so much about those particular 20 or 30 or 40 people who we ran through our lab study or who we contacted with our online survey. What we really care about is the population that those people represent, the population that those people were drawn from. And that's a lot of what we try to do with our research design, with our methods, and with our analysis, is kind of make that connection between the individual, small group of people we have in our sample and the broader group of people who we're really trying to make and test claims about. And I'd be remiss at this point if I didn't note that one of the real challenges of research design, again, thinking back to the previous class and the stages of the research process, research design and methods and analysis, one of the real challenges of research design is often specifying the scope of the population that we're studying. It's a frustration for me that often in psychology journals you'll read a paper and the authors will be kind of vague about who they're talking about. They'll say, we found this effect, or it seems to be the case that these two variables are related. And you wonder, for whom? Are we talking about for all college students because your sample was a college sample? Or are we talking about all people in North America who are English speaking? Are we talking about all people in the world? Sometimes authors are fairly precise, and that's great. Often they're not, and that's a criticism that's sometimes made of psychological research. So again, the interesting idea here is we're trying to focus on that population, although of course we can't gather all that data. We're always necessarily kind of making a leap from our sample to our population. And this is the important idea an important idea that I'm trying to get at in this portion of the lecture, is that the model is like a bridge. That's why I picked that picture, of course. The model is the bridge between the data that we have, that is the sample, and the data that we don't have, but which we care about more, that is the population. Now, in order to make that connection between sample and population, it's first important to understand the nature, the qualities of the data in that sample. You could easily imagine that having a well understood and high quality sample of data puts you in a much better position to describe a population of data than does having a kind of a poorly understood and confused and sort of low quality sample of data. So let's take a look at how this might work, what we would otherwise call in class descriptive statistics. And to do this, I'm using an example that I give in class. So if you're enrolled in my class, of course, you're familiar with this example. If you're not, just follow along as best you can, where I'm imagining a counseling center, much like the one on my campus right now, or indeed on most campuses, where students and other university folks go for psychological services of one sort or another. And in this lecture and in some of the following lectures, I'll kind of use a rather generic example of a simple independent experimental design where participants or clients at that counseling center are randomly assigned, let's hope it's randomly assigned, to either a treatment of some sort, maybe it's a particular drug, maybe it's a particular form of psychotherapy, or to a control group. Maybe it's a wait list group or some sort of non-therapeutic, just general support group or whatever. Then at some point down the line, maybe 6 weeks or 12 weeks later, the people in those two different groups are evaluated in terms of their level of overall psychological functioning, with the question being, is there a significant difference between the two groups? And by the way, I'm imagining, just because it's something that reminds me of the type of research that I did a little bit in grad school, that for our outcome or our dependent variable, we're using something like the global assessment of functioning, which is a pretty common, rather simple scale, which is used sometimes in clinical psychology and in psychiatry to get a sense of people's overall level of functioning. Higher values indicating better functioning, lower values indicating, sadly, worse functioning. And again, if you're taking my class, at this point, what we'd be doing is cracking open Excel and turning on the Excel analysis tool pack. And if you're not enrolled in my class, I encourage you to poke around in the menus on Excel, or indeed just look up online. Microsoft's got a lot of help files online about this, how to activate the Excel analysis tool pack. This is just a little set of tools which is sometimes handy for doing basic statistics in Excel. Now we're not going to use them a great deal in this lecture, but at this point in the lecture I like to give a little hint that, like, hey, this thing's out there, you might want to try using it sometime. The important idea here at this point is that the first step in data analysis usually is, or probably usually should be, to explore the data in the sample, to get a sense of what its shape is like, to get a sense of where its center or location is, and to get a sense of its dispersion or spread. Why is this so important? Well, we're trying to use this sample of data to estimate features of a population of data or populations of data, and we want to know how good those estimates are going to be. We want to know if, or we want to get a sense of if our estimates are likely to be fairly robust, or if they're likely to be fairly biased, which could be, of course, problematic. So what are the different types of descriptive statistics we could do? Well, there are lots of them, and you've taken other stats classes before, you've encountered many of these. I like to organize them into three sort of different domains, and the first domain concerns the shape of the distribution. If you're interested in the shape of the distribution of data that you have in your sample, you might, for instance, make a frequency distribution. You might make a table of the different values that occur for your outcome variable, like a little table just counting up the different values that you have. Or you might try and represent that pictographically with a histogram, which is just a graph of that frequency distribution or frequency table. So here's a little screenshot from Excel. You can see here what I've done is I've imagined all the participants in my data set. This is just fictitious data that I made up. You can see on the screen here, I think there are ultimately like 60 people in total, but half of them are in the control group and half are in the treatment group, and each person has a GAF score. And what I've done, just using some functions in Excel, is I've made a frequency table over here, looking at the number of people and the percentage of people who have a particular GAF score. So you can see a little bit more further down the line here. Just simply making that table or graphing a histogram. I actually don't think I have a picture of that histogram in this PowerPoint, but it's certainly in the spreadsheet workbook that I show my students in class, gives you a sense of the shape of the distribution. But just eyeballing that shape, saying like, oh, it looks kind of like one of those normal curves, or gosh, it doesn't, it looks like it's kind of lopsided or tilted, that's a good start, but we can get a little bit more precise, a little bit more numeric, and we can look at the skew and kurtosis of the distribution. Skew and kurtosis respectively refer to how asymmetrical the distribution is, if it sort of is weighted to one side or the other, that's skew, and how kind of sort of center heavy or tail heavy the distribution is. That's the kurtosis of the distribution. And Excel helpfully has these different functions, skew and kurt respectively, that give us those numeric values. Those numeric values might not mean a lot to you right away unless you know that a normal distribution is one that has a skew and kurtosis of 0. So the skew is pretty easy to see, which is that, you know, a normal distribution, a perfectly normal distribution, is symmetrical. It doesn't weight on one side or the other. The kurtosis is maybe a little bit harder to picture, but it basically refers to the idea that a lot of the data piles up in the middle, but then the tails extend out far in the distance on either end, on the positive end or the negative end of the distribution. So one concern that we might do, or we might have or consider in the realm of descriptive statistics, is what's the shape in an overall sense of the distribution, and maybe particularly, is it symmetrical or not? Is there evidence of skew or not? Another concern we might have is, where is the center of this distribution? Where is like the middle of it, for lack of a better way to describe? Well, this is pretty straightforward. You've encountered in other classes, surely, the mean, the median, and the mode. The important point to note here by way of a review is just simply that these are three measures of central tendency. They give us a sense of where the center of a distribution is, and they have slightly different properties. Now, in a perfectly symmetrical distribution, they are all going to line up together, so they'll all be good estimates of central tendency. In a skewed or lopsided distribution, they'll spread out from each other and may give you slightly different indications of where the center of that distribution is. In Excel, it's fairly easy to get the mean, the median, and the mode. There are different functions for them. Here are just the three that I use. By the way, if you're ever stuck for a function in Excel, if you hover your cursor over the little fx that you see kind of in the top margin above column C, that will open up the Excel function menu, and you can search pretty easily for functions. And you'll often be surprised in Excel, if you're looking for something, there's a very good chance that Excel has a function to do it. And so there are different ways, for instance, to measure the mode, and this is just the easiest or simplest one that I think you can use. So again, where we are is we're in descriptive statistics. One area of concern is the shape of the distribution in a kind of an overall sense. Another concern is the location of the middle of the distribution. The third concern is the spread or dispersion of the distribution. How spread out or not spread out is it? And that's pretty obvious, I think, what that means. But this picture hopefully illustrates that we could have dispersion, or we could have distributions which are quite tight, where most of the cases in the distribution have nearly the same value, or we can have distributions that are quite dispersed, where many of the cases have values that are quite different from one another. We want to understand kind of what the dispersion of our particular distribution is. Now here are some measures of dispersion that, like the measures of central tendency, you've certainly encountered before in other classes, but just by way of a quick review, the range, the variance, and the standard deviation are just ways of numerically calculating estimates, or I should say kind of indications of dispersion. So in our Excel spreadsheet, we could compute the range by subtracting the minimum value in the distribution from the maximum value. There are variance and standard deviation formulas, or functions, I should say, as well, which are what you see on the screen there. Now, if you're enrolled in my class at this point, we stop using Excel, or set Excel off to the side, minimize it, I suppose, and we crack open SPSS, which is a common statistical computation software that we use a lot in psychology. You're probably familiar with it if you're watching this video, certainly if you're taking my class. There are different ways to get descriptive statistics in Excel. I like to use the Explore module, which you'll find under the descriptive statistics sort of subheading in the pull-down menus. If you open up the Explore function, we can put our outcome variable GAF in the field called dependent list. You can click on the little button for statistics and ask for descriptive statistics. I also like to ask for outliers. You'll see why in just a second. We can click on the button for plots and ask for a histogram, maybe also a stem and leaf plot or a box plot if you want. And once you've done all that, you hit continue and hit OK in the main area, and you should get a fair bit of output. One of the pieces of output you'll get is a table that looks a bit like this. I actually noticed in the most recent version of SPSS the output looks a little bit cleaner and prettier than it used to. This is somewhat older, although the numbers are the same, somewhat ugly SPSS output. But here's some just basic descriptive statistics, and if you look at it closely and kind of squint your eyes, you can see, oh, there's the mean, there's the median, variance, standard deviation, the range, skewness and kurtosis, and so on. A couple things that might be kind of unfamiliar to you is there's the 5% trimmed mean, which trims off the top 2.5% and the bottom 2.5% of cases in the distribution to reduce the influence of outlying values on the calculation of the mean, because as you probably remember from just basic statistics classes you've taken in the past, the mean as compared to the other measures of central tendency is very sensitive to the presence of outliers. And here is our skew and kurtosis. I mentioned those already, so I guess that is not new, but it's also interesting to note that the standard error of these calculations is also given, and that's handy for reasons that we'll see in future lectures. Here's a table for the extreme values, which you can get. That's if you ask for outliers. It just SPSS simply picks the 5 highest and the 5 lowest values, reports the values of those numbers of the variable for those cases, and gives you the case number, which is just the place in terms of the ordering of cases that that particular case occurs in. So if you wanted to search them out, it makes it a little easier to find them. Now, why is this interesting? Well, it may not be, but it may be if you look at those values and see things which seem pretty unusual. Like, it may be rather unusual to see people with GAF scores in the high 40s in a college counseling center. That's pretty low functioning. So seeing those values, you might think, wow, is that a coding error or a measurement error? Maybe the person conducting the interview with those particular cases made a mistake when he or she was filling out the form for the GAF. Maybe instead of 46 they meant to write 64. This is one of those situations where, from kind of a research perspective, you might want to go back and check your notes or procedures. Maybe those are perfectly legitimate values, and those folks just unfortunately have really poor functioning. Likewise, it's maybe a little unlikely that someone's getting GAF scores in the 90s, although maybe not, but you might want to check those as well. Outlying values are always worth investigating. Simple point there, I guess. If you ask for the histogram, you'll get a histogram that looks a little bit like this. If you're familiar with SPSS, I've sort of double-clicked on this image here to open up the chart editor, and I've asked for a superimposed normal distribution curve, just to kind of illustrate that this distribution is not particularly normal in its shape. If it was, it would more closely line up with that line drawing there. So what's this all about? What's the important idea? Well, the important idea here is I think it's good to explore the data in your sample more or less before you do anything else. And recognizing that, you might ask, well, what is it exactly that we're looking for if we're exploring this data? Are we just kind of fiddling around? The answer is no, you are looking for some sort of particular things. We're usually interested in the center of the distribution because we're often in situations where we're trying to estimate some population mean based on a sample mean. So the overall population mean based on the overall sample mean, or we've got maybe the mean for the group that got a particular treatment versus the mean for the group that didn't get a particular treatment. At least in psychology, especially in experimental studies, we're often looking at means of different groups. And we know that means are rather sensitive to the presence of outliers. They're also sensitive to high levels of dispersion. We want to use these means, but if there's a lot of spread in the distribution, if there's a high, for instance, standard deviation, then measures of central tendency, especially the mean, may be somewhat uninformative. You know, I mean, if you think about this just kind of intuitively, if you take a class and you have a test and you ask the teacher, what was the class average? And she says, well, the class average was 82. And you ask, well, what's the standard deviation? If the standard deviation is 2 points, then that 82 is a pretty good indicator of where most of the people in the class scored on that exam. If the teacher says, well, the class average was 82, but the standard deviation was 12, now that 82 is less informative about how most of the people in the class did on that test. It's not uninformative, it's just less informative. So the analogy here is, if you had a data set with very high dispersion, all of a sudden you're a little less confident about those measures of central tendency than you might otherwise want to be. Another thing that you might be looking for is the sort of odd shape of the distribution. If the distribution is highly skewed, then again, measures of central tendency become somewhat problematic, or they become, more precisely put, they become biased. So you might imagine a case where, you know, the professor says something like the class average for this test was an 82, but there was a really strong positive skew, such that most of the people in the class scored in the 60s, but these couple people scored in the 90s, and that kind of dragged the average up. Again, in a highly skewed distribution, measures of central tendency are less informative than we might want them to be, or at least they need to be considered more carefully. I guess in that last little note, I hinted at an important thing that we're looking for when we are exploring data in our sample, is we're looking for outliers. Are there outliers in the distribution? We know that measures of central tendency, especially the mean, are highly influenced by the presence of outliers. Again, the easy example for college students, I think, is, you know, if you ask the teacher what's the class average, and she says, well, the class average is 82. Most people got, you know, in the 70s, but this one guy or this one girl, she scored a perfect score, 100. Now that outlier dragged the average up and made the average less representative of the overall body of the class than it is of this one student. So presence of outliers is worth investigating. And when you find outliers, or at least potential outliers, it's always worth asking, who are these outliers anyway? Like in the little example I gave before, you find someone who has a GAF score in the 40s in your college counseling center sample, and that's not impossible, but you might ask yourself, gosh, that seems kind of low. I wonder who this person is. Maybe this person is really from another population, and in that way, or in that sense, shouldn't be in the sample in the first place. You know, perhaps this person was not a college, a population member. You know, this is not a college person at the counseling center. It's someone else who is from a community mental health setting where, on average, psychological functioning is much lower, and he or she accidentally came to the counseling center that one day because, you know, she followed the wrong directions and went to the college clinic instead of the community clinic. And so that person, in a sense, really isn't part of the population you're interested in. College folks who go to a counseling center. His or her score is potentially biasing or influencing our estimate of whatever we're trying to study in that college population. Another another problem is maybe there was some sort of a measurement error, and I kind of talked about this already. You observe a low GAF potential outlier in your data set, and you think to yourself, maybe someone just made a mistake writing down information when they were recording this data. And it's one of the reasons why when you do conduct research of really any sort, it's important to have good laboratory notes or good field notes, so that if you find odd looking values in your data set, potential outliers, you can go back and try to interrogate them, which is to say, sort of investigate where they came from. Maybe you can find some evidence that they're outliers that could be reasonably corrected or changed or even deleted. Anyway, those are some important ideas to think about. With that in mind, I want to move on to the next section of my lecture. That section is called a simple model, and it's really just about that, a very simple model that you might make for data. And I'm kind of flipping back here to my example of the College Counseling Center. We have a treatment group, we have a control group. Ultimately, of course, we're going to be interested in what the average or mean level of functioning is in those two groups and whether or not there's a significant difference between the two. But for the time being, let's imagine that before we even compare the two groups, we're just interested in the overall level of functioning in our sample, regardless of whether the people were in treatment or not. Like, what's the average level of GAF in our sample? That's maybe a question that we have. Well, of course, it's not hard to compute the average for our sample. We could do it by hand, or we could have Excel or SPSS do it for us very quickly. The important thing to notice right here is that that mean is a simple, very simple model. By that, I mean it's a hypothetical value. It doesn't have to exist in the data set. If you took the average of all the GAF scores, you might get a decimal fraction which does not correspond to any individual person's GAF score. So in the sense it's hypothetical or abstract data, but it represents an average or a kind of a summation of the data in your sample. Also, it represents an estimate, potentially, of the population GAF score. Like, what's the average level of psychological functioning in the population of all people who go to college counseling centers? And that's, in that sense, it's a model, a very simple model. So let's go back to our old kind of generic formula. We see data. Data is the prediction that the model makes. So data equals model plus error, or we could write it out algebraically as data, which is y sub I, that's an individual person's observed score. In this case, their observed score on the GAF equals the predicted value on the GAF plus some amount of error to reflect the discrepancy between the two. So let's say our average GAF is like 62, and an individual person's GAF might be 72. So we write a simple equation like 72 equals 62 plus 10 to reflect how, or to apply that simple, rather generic formula to that one case. By the way, at this point, I want to make a slight sort of sidebar here that hopefully won't be too confusing. When you look across different textbooks, you'll see those algebraic formulas for models written sometimes in slightly different ways. So for instance, we sometimes write models with uppercase Greek letters, like this beta and this epsilon here. Usually when we do that, or when authors do that, they're writing a model to describe parameters in the population. So if you want to say, what's the model look like for the population, you kind of indicate that using uppercase letters. Whereas if you use lowercase letters, like these little ones here, you're usually trying to indicate that you're referring to parameter estimates. So the same formula might be written like, uppercase letters, meaning this is the formula for the population. Lowercase letters means this is the formula using parameter estimates of the population. Now, that distinction may seem rather slight or even kind of fiddly to you, and truthfully, textbooks I've observed, and I'll probably do this as well in my lectures, will sometimes flip back and forth between the two. But if you ever wonder, and I'm the type of person who would sometimes catch myself wondering about this, why did they sometimes use uppercase, why lowercase? Usually it's meant to refer either population level uppercase or sample level lowercase. Not a really important point, but one that I want to mention right now, because again, it'll come up later on in the class lectures or later on in the semester. Anyway, with all that in mind, let's make our little model, which is the mean. The mean, of course, is the arithmetic average, which is just the sum of all the values divided by the number of values. And you've seen this formula before in other classes. You could do this by hand. You could have Excel compute the mean for you, as we did previously. What you can do if you're in my class and you have access to the spreadsheet then is you can type in the predicted value from that simple model into each of the cells next to the actual data for each particular case in our data set. So you can see here participant number 1, who happens to be in the control group, has a observed score of 64, and we're going to click in the value for the mean for the overall sample. You could type that in by hand, or as you can see here, what I'm doing is copying from the cell that's further down and off screen where the mean is located. Now, if you're in my class and you have access to the spreadsheet and you do what I just described, you'll observe in the little scatter plot graph that's next to the table, a line will appear as you add in values for the mean, and that line is just simply the line representing the grand mean and representing this simple model. Now, this scatter plot looks a little bit weird because, well, the y-axis looks fine. It's the level of our outcome variable, global assessment of functioning. The x-axis is participant number, which is not something that you normally put on an axis in a scatter plot. I just did it here to spread out the data and make it a little easier to visualize. And you can see here that all these dots represent all the data points in the sample. I've colored them differently to indicate which ones are in the control group and which ones are in the treatment group. We're not going to get to that right now, but just observe that this line passes through that cloud of dots, and in that sense describes the cloud of dots. If you asked, well, someone walked up to you and said, oh, here's the data, I've heard you've gathered some data from a counseling center, what's the data look like? And you said, well, one person has 62, and the other person has 64, and the third person has 67, and so on and so on and so on. The person asking you say, no, just give me a description, give me the average. And you say, oh, well, the average is, well, whatever, it's, I think, 68 by the look of it. It's a way of summarizing the data we have and potentially describing or estimating data in the population that we don't have. And you can see just by looking at this line that it's a fairly good prediction, or I should say a good description of some of the data points. The line more or less passes right through or over some of the points of data, but it's a rather bad description for other points. There's quite a lot of error for some of those. The important idea here is that this sample mean is a model, that is to say an estimate for the population mean. And with that in mind, we can ask, how well does our model fit the data? Well, if we want to assess fit, a calculation we can make is the sum of squared errors, which is more or less what it sounds like. It's the deviation from the mean squared and then summed up. So if we take for each individual case that case's observed value for our outcome variable, subtract from it the predicted value, which in this case is the overall mean, square that difference to get rid of negative values, then add that resultant product to the next case and the next case and the next case, sum those all up, we've got the sum of squared errors. The important idea here is that sums of squares describe variability, and there are different kinds of sums of squares, and we'll use them a lot throughout this semester. Right now we're talking about a sum of squared errors, which is describing variability or error with respect to a mean. In this case it's the overall mean. And you can use this, or you can do this calculation in Excel. I guess there's nothing to stop you if you're just a YouTube watcher to create or copy this data, at least the data that you can see on the screen, into Excel and work along with me. But the basic idea here is for each individual case, I'm taking their observed value, subtracting the predicted value, which happens to be the overall mean, which is 68.23, squaring that difference, and then I'll do it to the next case and the next case and the next case, and at the very end I'll add them all up and get my sum of squared errors. Again, if this is not clear, just the error is the discrepancy between the data point and the prediction, which is the line. Sum of squared errors is just the sum of all of those squared errors. And if you sum all those up, you might ask, well, okay, this is just some large number, it's kind of hard to think about. What's the average squared error for this data set? What's the average amount of error for this model describing this data? Well, that calculation is really simple. That's just the mean squared error, which is just the sum of squared error divided by n minus p, where n is the sample size and p is the number of parameter estimates. So here you can see my sum of squared error formula divided by n minus p. N is going to be, I think it's 60 people. Parameter estimates is going to be 1 because we're estimating one parameter, the population mean. We're using the sample mean to estimate the population mean, so p is 1, n minus p is 59. We'll talk about this idea of subtracting parameter estimates a lot more in the next lecture, but suffice it to say, so far it's just going to be n minus 1. So here is my sum of squared error, which I talked about before. sample size is 1, is 60, parameter estimates is 1, so I can create the mean squared error pretty simply. Now, if all of this is sounding familiar, it's probably because you recognize that formula as the formula for variance. Variance is just the mean squared error for the simple model, where the simple model is just the group mean. So back in an earlier class, you've certainly encountered the formula for the mean squared error, where, for variance, which is, again, just mean squared error, where the model is the sample mean. So individual case data value minus the sample mean squared, summed up, divided by n minus 1, because there's only one parameter estimate. And if you want to see this, there's actually a function that you can do in Excel called var.s, and if you give as arguments for that function the range of data in column C, which is where it is in my spreadsheet, you'll get the same value as you got for your mean squared error. They're the same, and obviously if you're doing this quickly, you'd probably want to use the Excel function rather than, in a sense, kind of doing it by hand the way I did. I just did it that way to illustrate where these numbers come from, and why mean squared error is something that's useful for describing the average amount of error associated with this model, the mean, applied to this set of data. And also illustrate that, by the way, that's just variance. That's something you've encountered before. Again, something else you've encountered before is standard deviation. Standard deviation is just the positive square root of the variance, because variance is a value that is large, and it's not in the metric of, or it's not in the scale of the data itself. It's a little bit hard to figure, like, how big is a big variance versus a small variance. Standard deviation is in the same scale as the data itself. So again, if I had a test in my class, or you're taking a class and the teacher says, oh, the average is 82, the standard deviation is 4. Well, that's 4 units in the same scale as the test. So you're like, oh gosh, that means most of the cases, or most of the people in the class scored between 82 plus 8 or minus 8, which would be 2 standard deviations up or down from that mean. Okay, so are you with me so far? I hope so, because it's been a fairly long lecture. It seems like all of my lectures these days are clocking in at about an hour, and that's a long time. What have we learned? Well, hopefully we've learned a little bit about models. We've learned that models are just a general approach, or model building is really this general approach to data analysis. We're going to use a lot throughout the semester. Models are constructed to summarize or to describe a sample. They're done to represent or to estimate a population. And we can describe models in terms of their error, how much the model misses or doesn't miss the data, and in terms of their complexity, how many parameter estimates they use. And we'll talk about this a lot more in the next lecture, because these two qualities, error and complexity, are really, really important in statistics, especially the statistics of model construction and model comparison. So by way of a preview, next time I'll be talking a little bit about degrees of freedom, which are useful for describing a model. We'll talk about sampling distributions, which are just ways of thinking about different estimators, and ultimately I'll introduce basic hypothesis testing, which we'll be spending a lot of time with throughout this semester. So as I always say at the end of these recordings, thank you for your attention. I know it's a lot of time. Hopefully you've learned something, or this has been useful for reviewing if you're in my class and are watching these videos to review. Hopefully you have a little bit of time to make yourself a cup of tea or a cup of coffee, have a snack, and kind of refresh yourself for at least a few minutes. And when you're done, if you have questions and you're in my class, email me, put them on the discussion board in Blackboard, or talk to me in person. If you're just watching on YouTube, then hey, that's awesome, welcome, and post your questions or comments in the comment field. I'll do my best to monitor YouTube, and if I see a comment or question, I'll respond to it. Again, thanks so much, and I'll be back soon with another lecture about statistics and data analysis and all this cool stuff that we're learning about. So bye-bye.